Okay, I've been moving forward with what's called the second fundamental form. And in particular, I found this definition of L, which, okay, first of all, the variables u comma v are not, are plane variables that are not a tangent plane. Not tangent to curve at 0 comma 0. But so you basically have an arbitrary curve defined in the form r equals u comma v comma some z of u comma v. And so z represents the height of, or the height of the curve above the uv plane. Del r del u, r sub u, would be 1 comma 0 comma del z del v del u, and RV, and I'll just write that cross product here. RV is 0 comma 1 comma del z del v. And to do the cross product of these things, I should have said divided by the norm of the same thing. So to do the cross product of this thing, let me write it this way: 1 0 z sub u 0 1 z sub v, and then the let's see, u hat, v hat, and z hat up here. And then there's sort of a trick where I just kind of keep writing those things. I think I continue going this way for 1, u hat and v hat I write twice, and then 1 I write a second time. And then look for terms diagonal up is positive, and boy, I didn't do a good job of circling, but u hat times 1 z sub u plus v hat times 1 z sub v, v sub z, and then z hat is going to be negative because we got to move the circle in the other way. And so it's plus z hat times 1, or minus z hat times 1. So in a vector form, so rather than using the z hat, the u hat, v hat, and z hat, we'll just write this as del z del u, comma, del z del v, comma, negative 1. And that is the top part of it. What's the bottom part of it? The norm of that, which is just the square root of each part squared. So square root of del z del u squared plus del z del v squared plus 1. And that is our normal vector. And how does that work? Well, let's not talk about how it works just yet. Let's look at what this thing says when we've got r, let's see, this is r sub u right here, this is r sub v right here, and so we're going to take L, let's do LMN, and L is 1, 0, or no, 0, comma, 0, comma, del squared z del u squared. And so this is kind of a curvature of the z in the u direction. And then we're going to take that with dot producted with n. I'm going to save writing n for the end because n is kind of a long, n is, well, I could just drag it over. I'll go ahead and do it now. And del, and then the second one would be 0, 0, comma, del squared z del u, del u del v, and the third one was 0, 0, comma, del squared z del v squared. So really, it's 0 times this plus 0 times this minus 1 times this. So the final form of LMN is going to be negative del squared z del u squared over square root of del z del u squared plus del z del v squared plus 1. And you know what? I'm just going to write one big divide sign there because it's going to be negative del squared z del u del v and negative del squared z del v squared. So that gives us what L, M, and N are. Now the question is, how do we use L, M, and N? Because there is some ambiguity here, because there's just kind of like a random thing where they say second fundamental form is usually written as this. It doesn't really say like why or how. It says the matrix and the basis R sub u, R sub v of the tangent plane is this. I don't know exactly what that means. This sentence seems to have a little bit more substance to it. The coefficients L, M, and N at a given point in the parametric UV plane are given by the projections of the second partial derivatives of R, so that's these, at that point onto the normal line to the surface, onto the normal line of the surface, and can be computed with the aid of the dot product as follows. So I want to think about this thing a little bit. We've got projections of the second partial derivatives of R of u comma v is a regular parametrization of a surface in R3. So projections of second partial derivatives of the regular parametrization R of u comma v of, so I got projections of the second partial derivatives of the regular parametrization of the surface in R3. What is that second partial derivative? It's like del squared z del u squared del squared z del v squared and del squared z del u del v. But more specifically, there's 0, 0, del squared z del u squared, 0, 0, del squared v del v squared. It has a direction to it. Think about it. If z of u looks like this, then right in here, you're going to have negative curvature. You're going to have right in here, let's see, right in here, you're going to have positive curvature. Right in here, wait, from there to there, you're going to have negative curvature. I got to put that positive curvature a little further up. There's your inflection point. You got positive curvature there, negative curvature there. Got positive curvature here, and maybe there, and then a little bit of negative curvature there, and definitely through here. It's kind of skippy because I didn't draw it very well, but negative curvature in the spots where it's concave down, positive curvature where it's concave up. Now, but this is weird because these are going to form vectors representing what, though? A vector pointing which way? And